Good evening, sir. Good evening to one and all. This is Meena. I am from ECB section. My roll number is 23401. Today, my topic is Wiener-Khinchin theorem for cross correlation and cross spectrum. Introduction to Wiener-Khinchin theorem. The Wiener-Khinchin theorem is fundamental in the field of signal processing. It establishes a relationship between the autocorrelation function and power spectral density. This theorem also extends to cross-correlation and cross-spectral density, which are crucial for analyzing multiple signals. Densities definitions of key concepts. Cross-correlation measures the similarity between two signals as a function of time lag. As a function of time lag applied one of them, the cross spectrum represents the frequency content of the cross correlation, providing insight into how signals interact in the frequency domain. Understanding these terms is essential for applying the Wiener-Khinchin theorem in practical scenarios. Mathematical formula of cross correlation. The cross correlation function is or suffix of xy into by tau is defined as the expectation of the product of two signals x of t and y of t plus tau. Mathematical this is expressed as or x of tau or exponential of x of t plus y of t plus tau. This formulation allows us to analyze how the two signals related to each other different time lags. Power spectral density. The power spectral density describes how the power of a signal is distributed across different frequencies. The power spectral density can be applied from the Fourier transforms of the autocorrelation function. For cross spectral density, the Fourier transform of the cross correlation function gives insight into the frequency relationship between two signals. Wiener-Khinchin for cross correlation. The theorem states that cross spectral density can derive from the cross correlation function, especially s of xy of f int or xy of tau and j2 by minus j2 by pi into f tau d tau. This relationship simplifies the analysis of the interaction between two signals in the frequency domain. Properties of cross spectrum. The cross spectrum S of x y f reveals how much of the signal is x of t contributes to the signal of y of t at each frequency. It is a complex valued function that provides both magnitude and phase information about the relationship between the signals. Understanding these properties can assist in tasks such as filtering and signal reconstruction. Applications of the Wiener-Khinchin theorem. This theorem is widely used in engineering fields, particularly in signal processing and telecommunications. It helps in analyzing system responses and designing filters based on the behavior of input and output signals. Additionally, it can be applied in data analysis for noise reduction and feature extraction from multiple signals. Limitations of the theorem. The Wiener-Khinchin theorem assumes stationarity which may not hold for real-world signals. Non-stationary signals can lead to inaccurate interpretation of the cross correlation and cross spectrum. Therefore, modifications and alternative methods may be required for ascent. Summary of key points. The Wiener-Khinchin theorem provides a powerful link between two domains and frequency domain representation of signals. Understanding the relationships encapsulated in cross correlation and cross spectrum is essential for effective signals analysis. This theorem has significant implications across various fields including communications, audio processing and biomedical engineering. Future directions. Future research may focus on extending the theorem to non-linear and non-stationary signals. Incorporating machine learning techniques could enhance the interpretation and application of cross-correlation and cross-spectral analysis. Continued exploration of the theorem's applications in emerging technologies will be crucial for advancing signal processing methodologies. References: Pauli's 1991 probability, random variables and stochastic process, MS Grohill, Oppenheim, AV Carey RW, 2009 discrete time signal processing Pearson, uh, Procus JG, Manolekis, DJ, 2007 digital signal processing principle, Agarthas and application Pearson. Thank you, sir.